All right, welcome back, everybody. It is Mr. Youngren once again, and we are going to continue our work in Unit 8. But this time, we're going to actually introduce what the heck a log is. And we're going to actually take just a real kind of basic approach to it, as it is a very new idea to everybody in here. So we're going to start on page 178. And when we get to 178, just like always, there's an opening problem. So I'm going to ask that you take a second to try to figure out this opener. And really all I'm wanting you to do is try to figure out what do the exponents need to be in order for these equations to be equal. Some of them are going to be pretty obvious. Some of them you might have to think a little bit, or even maybe grab a calculator and guess and check until you get them to work out. But go ahead and hit pause, excuse me, see if you can find the solutions to the opener, and then hit unpause when you're ready to check your work. All right, well, here's what you should have gotten. And like I said, some of them were pretty clear, especially the first one, because we know that 3 to the power of 2 is 9. So in this case, we would need x to be 2 in order for both sides to be equal. Next one, still fairly straightforward, but maybe not an exponent that we're too familiar with. 2 cubed, or 2 times itself 3 times, is going to give us 8. So we'd want that exponent to be 3. Now over here, some of you might look at that and say, what the heck, how do I get fractions with exponents? Well, actually, if we make an exponent negative, that changes where that base is. And so if I take 3 to the power of 3, that's 27. But now if I make that exponent negative, it's 1 over whatever that value was. So in this case, we want x to be -3 so that both sides are equal. Now, the one that's most tricky is this last one, because if I start putting in whole numbers, I know that 4 to the power of 1 is 4 and 4 to the power of 2 is 16, but there's not a whole number that's giving me 8. So I'm kind of having to estimate, or at least right now with the tools that we have. And so I'm like, okay, 8 is kind of, it's, well, definitely in between 4 and 16, a little bit closer to 1. So you might have to just kind of roughly estimate where that might be, which is actually, it comes out to be exactly 1.5. Now, I shouldn't say about 1.5, it is 1.5. I don't expect us to know how to come up with 1.5 exactly, at least not right now. You might have had to guess and check, but by the end of this lesson, you're gonna know how to come up with that. So let's jump into it and let's talk about how in the heck can I come up with that answer there, and is there an easy way to find it? The answer actually is yes. So in general, every mathematical operation in math has an inverse operation, right? Adding undoes subtraction, multiplying undoes division. One that we've talked about somewhat recently is with quadratics or squaring something, square rooting, right? Everything kind of has an opposite or an inverse operation. The inverse operation of an exponent, if you can guess based on the title of this unit, is a log. So let's look at what a log really is. And it's really kind of similar to an exponential, but it's just kind of like, I guess the opposite. So let's take a look at it. So the first thing that we're gonna do to introduce logs is we're gonna make a table of values of 2 to the power of x, which is an exponential, and we're gonna actually graph that, because we're gonna use that to then help us graph the corresponding log. So 2 to the power of x, if I take 2 to the power of -3, I already know it's going to be some kind of fraction or decimal. That's 0.125. Yeah, let's write it as a decimal as well. This would be 1 over 8, which equals 0.125. 2 to the power of -2 would be 1 over 4, which is 0.525. Let's fix that. There we go. 2 to the power of -1, that would be 1 over 2, which this time that's 0.5. Anything to the power of 0 is always 1. That's one thing we like to forget and call that 0. It's not 0, it's 1. And then from there, it's pretty easy, right? 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8. So we can go ahead and plot these. We could have used the rules that we talked about in the last video as well. But -3 is 0.125, so barely above. -2 is 0.25, just barely above that. -1 is 0.5, so barely above that. And I got 1. And then 1, 2, 2, 4, and 3, 8. And so here's what the exponential would look like. And so now if we go and flip the page over to 179, There we go. It's now asking, let's create the graph of the inverse of f of x from the previous graph. And it says start by creating a table of values and then plot the points to drop. Now we've done this before, where if we have a function and we want to graph its inverse, we're essentially going to switch the domain and range. So if I'm wanting to take this previous table to help me find the inverse, which we don't know what that equation is yet, really all I'm going to do here is take the original x values, and those are going to become the range, and my y values are going to become the x's or the domain. So I'm just switching where those are. So I have 0.125, 0.25, 0.5, 1, 2, 4, and 8. And then the x's become the y's. So making this -3, -2, -1, 0, 1, 2, and 3. And so now when I plot these, that's going to create the inverse of that 2 to the power of x, which we can actually come up with an equation shortly. But this is going to be the first graph we see of a log function. And so you're going to see it has a similar shape to that exponential, but actually just a little reversed. So x 0.125, so barely above, I need to go down 3, barely to the right. 0.25, barely to the right, but down 2. 0.5, so a little more to the right, just down 1, and then 1, 0, and then 2, 1, and then 4, 2, and then 8, and 3. And there is the graph of the inverse of 2 to the power of x, which actually, if we were to write the equation, f of -1, or the inverse of that function, and what you just graphed is log base 2 of x. And so that's where logs come from. It is us doing the opposite of an exponential. And if we look at these graphs, right, from what we did on the last page, from what you're seeing here is your inverse, it's really the same, just kind of shifted along. Well, actually, technically, it is reflected across the line y equals x. So we've basically taken this graph and we're folding it over to create our new graph down here. Now, that's just an introduction. So don't think that's something that you're going to need to do exactly. We are going to graph logs, and we'll have rules for that, just like we do with most of our graphs. But let's talk about domain and range of these, because that's something we've kind of done with every unit. So looking at 2 to the power of x, so that's the first thing we looked at on page 178. If I were to look at my domain here, and with exponentials, that's all reals, or from -infinity to +infinity. Right? We've now talked about multiple ways of how we can write domain and range. This is an interval notation. The range, however, is limited. It's limited in 2 to the power of x because I can never get a y value to be negative. And so because of that, we get that horizontal asymptote here. And so our range is only from 0 all the way to +infinity. Now, what's really important here is we never get to 0, right? I have that horizontal asymptote here. And so we'll get infinitely close to 0, but we will never touch it. So it does need a curved parenthesis, and then it's going to go all the way to infinity. All right, and what is the equation of the horizontal asymptote? That would be y equals 0. So now when we get to the inverse, everything's just the opposite. So the domain of the inverse is what our range was originally. So these y values became our new x values. So that's going to be from 0 to infinity. Do we see that on the graph up here? Definitely. Okay, in fact, there is a vertical asymptote right here telling us that the graph will not go further left than 0, and it goes all the way right to infinity. Just like with that horizontal asymptote in the exponential, I'm never going to touch this asymptote, so we're going to put a curved parenthesis on 0, and it goes all the way to infinity. So our original range became our new domain. And you can probably guess it, the original domain becomes our new range. So -infinity to +infinity. Now, if I look at the graph, I can clearly see it going down pretty quickly. And as it goes up, it's going up very slowly. It almost looks like it's getting flat, and it kind of is, but it's still growing just really, really slow. So it will keep moving all the way to infinity, just we would need to plug in really big x's in order for it to get there. Right, and the last thing, what type of asymptote does our inverse have? It has a vertical asymptote. So a VA, a vertical asymptote, and that vertical asymptote is at x equals 0. So everything's just the opposite, which we should expect with inverses. So now that we've kind of seen what a log is and where it comes from, let's talk about a couple things with this. So now what do we call the inverse of an exponential function? I've already said this multiple times. It is a log or a logarithm. I'm just gonna write log. This I already talked about, how the domain and range switch. And so one thing that's really important here is every time you see an exponential statement, like 2 to the power of 3 equals 8, there is a corresponding log. And it actually works both ways. If you see a log statement, there is a corresponding exponential because they're inverses of each other. And so one thing that we need to be able to do is if I give you an exponential statement, can you come up with the corresponding log? Or if I give you a log, can you come up with a corresponding exponential? This is the key to the whole unit. If you can convert between an exponential into its corresponding log and vice versa, you're going to be able to solve these equations. You're going to be able to do so much with this. This is really the key to the whole thing. So let's take a look and try see if we can't come up with a clear way of how to do this. So I have an exponential here, and I want to write a log. Here's how I remember how to do it. I start by writing the word log. Every log or every exponential has a base. Same thing with the log. And guess what? Those bases are the exact same. So we're going to say this is a log with a base b. That exponential is base b. And then the last thing that we do is I say that I switch the location of the other two terms. So instead of it being b to the power of x with my log, I want it to be b and then have the y on that side. And then it's equal to x. And so I can check this really easily. If I hide the word log so that I don't see that word at all, wouldn't you agree that this looks like an exponential statement? This looks like b to the power of y equals x. And so that's an easy way for me to check to make sure I did this right. Are the bases the same? Yes, it's still b. And did I switch the position of the other two terms? Absolutely, because instead of it being b to the power of x, it's now b to the power of y and it equals x. So the only thing additional is now we have that word log there. So using your own definition, describe how to change an exponential equation to a log. Know that this works both ways. I'm going to write down my definition, which you feel free to use. If your teacher has another way, you can write that down there. Or if you have another way, feel free to write that down as well. So I always say the base stays the same. So that's whether we're going from exponential to log or log to exponential. The base of the log becomes the base of the exponential. The base of the exponential becomes the base of the log. And then the last thing is we need to switch position of the other two terms. Now that's very broad, right? It's not super clear. But I think as we start to see some examples and we see how those x and y terms, and when we actually give them values, how they shift, it becomes pretty clear. Now, again, your teacher might have a different way of how to write their own definition. You might have a way that works for you. There's no right or wrong answer here. But the bottom line is you need to be able to convert between exponential and logs. And it's really quick, and it should be really easy once we get the hang of it. But because it's new, it does take some getting used to, and it does take some practice. So before we actually start doing this, let's talk about just two kind of special logs. One thing that I went really quick through is how to read a log. So how we would read this is we would say log with the base b of y equals x. So log base b of y equals x. So in certain cases, we don't write the base of a log. So if you see something where this is like log and there's no base there, that's technically a log with a base 10 of 100 equals 2. And again, you can see how this conversion might work out. If I hide the word log here, I see this as 10 to the power of 100. So I've switched the 100 and the 2, and it equals 2. So the bases are the same, but the 2 and the 100 have been switched in terms of where they're located with the position. The next one, we talked about the number e a couple lessons ago. This, if we ever see a log with the base e, this is called the natural log. And so if we have something like e to the power of 4 equals e to the power of 4, that should be obvious, we can write it as a corresponding log. Now, what I want us to write down, I don't know that this part is all that helpful, is that a log base e of x is equal to the natural log of x. Okay, those are the exact same. And that's really important that we make that connection. So sometimes if I see this ln that reads natural log, I might just automatically convert it to a log base e. I really like being able to physically see where that base is. So a log base e is a natural log. Once again, if you see a log without a base, that's log base 10. We're going to see this a couple of times as we work through these. So using our conversion between a corresponding log and exponential, we are able to come up with values of logs without the calculator. We are going to talk about how to do it with a calculator, but without a calculator, we can come up with this pretty easily. And we're going to have to do that conversion as to what I showed up here. And guess what? If we're going from log to exponential, the rule is the same. So what I do is I hide the word log, and I go, okay, my base needs to be the same. So it's still 2. But instead of it being to the power of 64, now it's to the power of x. So 2 to the power of x equals 64. And I check, is my base the same? Yes, it's still 2. And did I switch to the position of 64 and x? I sure did. And what I can do is I can figure out 2 to what power is 64. Might take some guessing. I know that 2 to the power of 3 is 8. So maybe I try 5. Oh, 1 short, so 2 to the power of 6. There we go. And it gets x equals 6. So I'm able to get the value of logs by using its corresponding exponential. We're going to actually do the opposite here in just a little bit. So let's do, let's actually look at, let's just do one more. So this last one, number 2, if I had the word log again, I'm going to take 7. I'm going to switch the position of where the 49 and x are. So now it's 7 to the power of x, which equals 49. And this one's pretty clear. This means that x is just going to be 2. You know what? Why don't we just do all of these? It'll take us real quick. All right, so continuing along, I know I need to switch the 1 and the x. 9 is the base, so it's 9 to the power of x equals 1. We need to remember that anything to the power of 0 will always give us 1, so x needs to be 0. And then the last one, my base is 1/3, so that's still the base of my exponential to the power of x. And we want it to equal 1/27. There's something that we can do that's going to be really useful for some problems we see later that makes this a little bit more clear. Some of you might be able to look at this and go, yeah, okay, that exponent's 3, but a lot of us are going to look at it and go, I have no idea how to find that. But here's what we can do. 1/3 and 1/27 can be written as a similar base. 1/3 is really equivalent to 3 to the power of -1. So it's 3 to the power of -1 times x. And if I'm doing 3 to the power of -1 to the power of x, that's really the same thing as 3 to the -1x, where I'm just multiplying those exponents. Now that's equal, 1/27 is equal to 3 to the power of -3. And so I could check that on my calculator. 3 to the power of -3 is 1/27. Well, it gave me a decimal. I can hit math, enter, enter. Tells me a fraction, 1/27. And so now I'm like, okay, the bases are the same. When I think about what it means to be equal, they need to be the exact same on both sides. And so if I wanted to solve this, I would just take the exponents, -1x, and set it equal to -3 and solve that, where I would divide by -1. And I get x equals 3. So this is a long way of me getting to that answer. But in fact, this is going to be one way of how we can come up with that answer. And it's actually how we could have come up with the answer in our opening problem in this bottom right problem. So this is going to be a really useful way, and you're going to get more practice with that later. All right, so a couple more things. Let's just do, I think that's it. Let's go ahead and stop right there, and you can pick up this work with your teacher from here. So as always, make sure you complete your video check-in, and if you have any questions, feel free to reach out to your teacher, and have a great rest of your day.